Hello everybody, and welcome to the next lecture of 6838. Today we embark upon the next big chunk of our course, which really involves building up machinery for a very particular approach to shape analysis that's extremely popular across different domains. Now, the basic approach here is going to be what we call operator-based. What that means is that we're going to spend quite a bit of time understanding the structure of operators on functions. So for example, the main operator that we're going to study is an object called the Laplacian, which takes in a function on a manifold and outputs the function which is the second derivative of the input at every point, multiplied by -1, which is a sign convention that I've chosen in this course. And what we'll see is that by computing the eigenvalues and eigenvectors of these operators, we're able to infer a lot of information, but not 100% information about a shape or a manifold more generally. Moreover, after building up discrete Laplacian operators, what we'll see is that suddenly we've enabled a huge number of different applications that essentially all follow the same outline of find some matrix approximating the Laplacian, do pretty straightforward linear algebra, and then read off an interesting piece of geometric information from that calculation. And the really exciting and cool thing is that we can apply exactly these same calculations to do low-dimensional geometry, for example, in surface smoothing, parametrization, some other applications there, that are going to apply to high-dimensional geometry, for example, in semi-supervised learning, basically without any change. So this is one of these sledgehammers of shape analysis that's worth understanding in a lot of detail. Now, before we start our journey into the Laplacian operator, I thought I'd preface with a few warnings for the students in the class. The first one is that sign mistakes are going to be extremely likely in the coming couple lectures on the Laplacian. And I'm just going to warn you about this right now rather than, I don't know, clean up my lecture content. Here's the thing, between mathematics, physics, and computer science, there isn't a clear convention on the sign of the Laplacian operator. Namely, we'll see that the Laplacian is the sum of second derivatives, or minus the sum of second derivatives, depending on what textbook you read. In this class, I'm going to try to stick to the convention that Laplacian has positive eigenvalues, or at least non-negative eigenvalues, meaning that it is minus the sum of second derivatives. That way, when we discretize it, it'll become a positive semi-definite matrix, which is convenient for linear algebra. But because I'm working from a lot of different papers and textbooks at the same time, it's likely that I'll make many sign mistakes in our discussion. So, you know, in your mind, just put a plus or minus in front of any term involving Laplace operator. And incidentally, I would encourage you to do the same thing when reading research papers in this area. There are many papers out there, I won't name any by name, that maybe the sign of the Laplace operator actually changes depending on what section you're reading. Essentially, all of us are pretty sloppy about it, but the good news is that debugging your code is pretty straightforward. You know, if your code is misbehaving, you can try multiplying your Laplace matrix by -1, and 95% of the time that'll fix it. I know that's not the kind of thing that I should be telling you as a professor in this area, but that's the sort of the reality. The other warning that I'll give you guys is to fasten your seatbelts here. We're going to do a lot of sloppy math in the coming lectures here. My goal is not to build up the theory of the Laplace operator from the ground up, including function spaces, differentiable manifolds, and so on. Unfortunately, in 6838, we simply do not have the time to do that. However, what we can do is sort of a bunch of informal calculations to give you a good feel for how the Laplace operator behaves and how it's constructed, even if we skip over some of the technical things that you really should do to have a morally justified definition and set of manipulations for this operator. So throughout this course, if you guys ever need pointers to more careful mathematical treatment, I'm happy to give that to you. The reality is that the Laplacian is actually not an object that you typically see in your undergrad intro differential geometry class. It's a bit of a delicate object to work with if you want to be extremely rigorous about it mathematically. But it's also an object that is extremely applicable in many different algorithms. So we're going to walk kind of a tricky line here and just take an intuitive approach for now. And I think that's pretty typical. Okay, so now that I've hopefully not scared you away from the content of the coming lectures, let's get started here. So our story begins with a really famous research paper in mathematics. I don't remember the year. I think it was around the 1960s. And it had this really, I guess, kind of attractive title that really stuck around in the mathematical community. This turns out not to be the first research paper on this topic, but it is one of the more memorable ones. And the title of this paper was, "Can one hear the shape of a drum?" And this was phrased as a question because at the time, we didn't have a positive or a negative answer to a pretty simple question which really confounded folks for quite some time. So rather than following the mathematical derivation in this paper, let me give you a bit of intuition for what this "can you hear the shape of a drum" question is really asking. Now, in particular, what we can do is set up an experiment. And here's the experiment that we do. Here we've got an animal playing on a drum set, and all of the students in 6838 are listening to him play. But they're looking away from the TV screen. So you don't get to see the musician as he's playing the drums. All you get to do, because your eyes are closed or you're facing away, is hear the sound that the drums are making. Now, obviously, different drums make different sounds, right? If you have a big bass drum, it makes a loud, low tone. If you have some very small, tight drum, it probably sounds higher, maybe has a shorter decay, whatever. And the question is, if the only thing that you hear is the sound that the drum makes, can you reconstruct the shape of the drum? Or maybe the two-dimensional version of that is, can you reconstruct the face of the drum? Which is probably roughly accurate for this experiment as I've described it to you here. So again, the basic question here is, can I reconstruct a piece of geometry based on an audio signal? And this is one of these questions where when you hear it, it kind of sounds ridiculous. Like, no, obviously you shouldn't be able to do that. And then you think about it a little bit more and it becomes unclear. And then you think about it even more and prove some theorems and then it becomes clear again. So originally this sounds like a totally impossible task, right? You know, the audio, you know, the sound signal that your ear is receiving is like a list of frequencies, right? It's a list of different vibration modes that are coming off of the shape. So you don't see the geometry vibrating. All you do is hear the frequencies that are coming out of the drum and into your ear. And somehow that feels like a one-dimensional signal. But on the other hand, your sense of sound is really good. You can distinguish between different objects falling on the floor even if you didn't see it happen. I can tell you, I drop things on the floor all the time. And in fact, if you go to some really, really simple examples, you'll see that there are intricate links between geometry and audio or vibration. So the simplest version of this is one-dimensional. Some years when I teach 6838, I bring in my cello and try to demonstrate, but I tried with these lights. It didn't work terribly well. So here's one way that you could understand a one-dimensional version of the "can you hear the shape of a drum" question, which is, I have a guitar. You know, guitar is strung with a bunch of strings. And I want to know the length of a string based on the tones that I'm hearing. You know, based where the string is vibrating. So that would be the one-dimensional version of this problem. If I know the vibration frequencies of a one-dimensional string, in this case with Dirichlet boundary condition, right? The string is pinned at the two ends against the bridge and the nut at the top of the fingerboard. If I know the vibration frequencies of that string, can I reconstruct its length? And it turns out the answer is yes, right? And I think we all know this intuitively. So if you see somebody play the guitar, you know, how do they control the pitch of the tone that comes out of the guitar? Well, they push down the string with their fingers, and as the string is shorter, right? So as you press your finger closer and closer to the bottom of the instrument here, the pitch raises. So let's think about that geometrically. Essentially, the intuition here is that as we decrease the length of the string that's vibrating, right? So length is a geometric signal. The list of frequencies that we hear becomes higher. They become higher in pitch. So there actually is a relationship between the length of the string and the vibration frequencies that you hear. In fact, the answer to can you hear the length of a string is yes. If you know the pitch that it's making, vibration frequencies, and you know it's a one-dimensional object and a little bit about the physics, then you can actually figure out the length of the string based on the sounds that you hear. Unfortunately, this one-dimensional piece of reasoning, well, it actually does hold some water in higher dimensions. The answer to can you hear the shape of a drum is no. ... but ... So in particular, the answer is that there are drums that are isospectral, meaning I can find two drums out there in the universe that make exactly the same vibrations into my ear. In fact, it's disappointingly simple, the counterexample. So here's one on the screen here. But that said, pairs of isospectral drums are extremely rare. They have to be constructed in a very careful fashion. It has to be a relatively weird drum. So this sort of informal thing here is the spectrum of vibration frequencies. The list of frequencies that an object vibrates at naturally tell you a lot, but not 100% about the piece of geometry. And so this perspective, this idea of spectral geometry is the phrase, has been extremely important in the applied geometry world as a toehold into ways of carrying out shape analysis. One thing I should note, by the way, every time I teach this course, I offer extra credit to students who manufacture these pairs of drums and actually carry out this experiment, and I've yet to have a student actually do it. But maybe this is the year, you know, if you make these isospectral drums and actually show all the other students that they make the same sound. I think that would be pretty fun. Okay, so the rough intuition for this area of spectral geometry is that you can learn a lot about a shape by hitting it lightly with a hammer. Now, our goal isn't to shatter the object, that's a whole other type of physics, but rather, you know, if I think of our bunny here as being made of some nice isotropic, infinitely thin material, and I hit it with a hammer, what's going to happen is that I can decompose the vibration modes of this object into a list of frequencies and eigenfunctions. And that list of frequencies is going to tell me quite a bit about the geometry of the shape. And so there's this intricate link between geometry and physics that we're going to leverage to design really practical algorithms in the shape analysis world. Now, many of the pictures that we're going to draw, especially in today's lecture and the next one, will be two-dimensional, or at least intrinsically two-dimensional. And that's because, you know, we're all looking at a two-dimensional computer screen right now. But I'm going to try and keep our calculations, for the most part, applicable to a k-dimensional manifold embedded in Rn. I think actually the standard that I use is m-dimensional manifold embedded in Rn. And we'll see that Laplacians on higher dimensional objects are extremely valuable as well. Okay, so this is the tip of a giant mathematical iceberg. Essentially, there's an entire area of mathematical research which continues to be quite active and is fairly modern in the mathematical scheme of things, known as spectral geometry, which asks the question of what we can learn about a shape based on its vibration frequencies and oscillation patterns. So what we're going to see is that we can compute these vibration frequencies based on a particular operator known as the Laplacian. I've already thrown around that word quite a bit, but we're essentially going to spend all day today and probably some of next time actually deriving what this object should be. And by just knowing the list of eigenvalues of the Laplacian, we already can read off quite a bit about geometry. And we're going to learn even more about geometry if, in addition to that, we can observe the actual eigenfunction, which is like the pattern of up and down vibrations on the surface that happen in response to one of these eigenvalues. So this is a tough sort of operating system to build up from the ground up based on the machinery we have in 6838. I mean, essentially all we've done is define manifolds that are embedded in Rn and some basic curvature and geodesic computation. So we're going to have to follow a pretty lengthy path to get from 0 to Laplacian in today and our next 2 or 3 lectures here. So here are our objectives for today's lecture. Essentially, we're going to take this idea of vibration mode and make it more precise. And we're going to do so by considering progressively more and more complicated domains. We'll start by formalizing that can you hear a shape of a line segment problem and basically working through that completely in both the discrete and smooth cases. Then we'll bump up to regions in Rn. So these are still flat, but they're higher dimensional. We'll take a step sideways and talk about a discrete structure, namely a graph, a collection of vertices and edges. And then finally, we'll do the big one, which is surfaces and I should really say submanifolds of Rn, where we can define the Laplacian operator in its full glory. Then in the next couple lectures, we'll cover how to discretize this object both in low and high dimensions. Right? So remember the low dimensional Laplacian we can do on a triangle mesh or something like that, and we'll see the high dimensional Laplacian we can do on a point cloud. And then we'll conclude with many, many different applications, essentially of just this one construction. We'll see that if we have a piece of code for computing or approximating a Laplace operator, suddenly we've opened the door to state-of-the-art in many different applications of shape analysis. So to get started, let's do a little bit of terminology review and basic mathematical review, and then we'll dig right into the details. So we're going to need a lot of different machinery that we've used already in this course. The main one that's going to come up throughout our lectures here is the idea of a vector space and a linear operator. And this is going to be the point where we really have to be grown-ups and think of linear operators as things that look like this object L I show on this slide, right? That essentially a linear operator is something that satisfies these two axioms shown in yellow. We showed in the second lecture of this course that we can think about linear operator as like matrix vector product in the finite dimensional case. But now we're going to talk about infinite dimensional spaces of functions. So while the linear algebra college picture may give us good intuition and is going to play out when we discretize our operators, it's a tiny bit dangerous to resort to the matrix vector product picture immediately. So I'm going to try and avoid that as much as possible to get started. In particular, I think our college linear algebra class mostly lives upstairs, right? Like talking about matrices and vectors. Instead, we're going to think about this sort of dual object, this linear operator, which is a function that kind of takes x to a times x in the finite dimensional case, but in the infinite dimensional case, just satisfies those two assumptions on the previous slide. Now, the other object that we're going to need is something that you probably saw in your linear algebra course, but if not, we'll go ahead and state it here, which is the spectral theorem in Cn or Rn, either one is fine. Remember, C stands for complex numbers. And the theorem, in all of its glory, and with a lot of color coding, is shown on the slide here, which says, suppose that I have a matrix A, which is Hermitian. Right? So that means in the real valued case that A is symmetric, and in the complex valued case that A equals its conjugate transpose. Then we can conclude a lot of things about our Hermitian operator. We know that it has an orthogonal basis of n eigenvectors. And moreover, we know that if A is positive definite, then the corresponding eigenvalues are non-negative. Now, just for fun, as a linear algebra warm-up, I thought I'd derive the easy pieces of this spectral theorem here, just for real-valued symmetric matrices. Now, the first one has to do with the orthogonal basis of eigenvectors. And in particular, what you would need to show is that if I have two eigenvectors corresponding to distinct eigenvalues, they are necessarily orthogonal. So we're not going to show that the set of eigenvalue vectors is complete, like there's n different ones, but we're going to show we can take any two eigenvectors and assume that they're perpendicular to one another. Incidentally, if they have the same eigenvalue, we could just do that by Graham-Schmidt orthogonalization. So the real case that we have to worry about is when there are two different eigenvalues involved. So let's do that really quick. In particular, let's say that I have a symmetric matrix A, and I know the following. I know that AX equals lambda x, and I know that AY equals mu y, where x and y here are non-zero eigenvectors of A. Okay. Well, in that case, what do I know? Well, I can actually derive that they're orthogonal using kind of a sneaky trick. So we're going to look at the quantity lambda times x transpose y. Remember, if they're orthogonal, then x transpose y should equal 0. That's going to be what we show. Oh, and we need one more assumption, which is lambda does not equal mu, because when lambda equals mu, we can just orthogonalize them manually, and that's fine. Okay, so in any event, let's start here. So we have lambda x transpose y. Well, we know ax equals lambda x, so this is the same as ax transpose y, which is the same as x transpose a transpose y just by linear algebra. A is symmetric, so this is x transpose ay, but ay is equal to mu y, right? So this is equal to mu x transpose y. Okay, so if we subtract the right-hand side from the left, we get that 0 is equal to lambda minus mu x transpose y, but we know that lambda is not equal to mu by assumption, so we can divide by lambda minus mu because it's non-zero, and we get x transpose y equals 0. So what we showed is that if we take eigenvectors corresponding to different eigenvalues, they necessarily must be orthogonal to one another. One thing that you should check later on in this lecture is that there's nothing about this proof that needed our vector space to be finite dimensional. Really, x transpose y here was just a stand-in for an inner product. So the same thing is going to be true for Hermitian operators, which are ones that sort of satisfy that like x, a, y is really the same as a, x, y, right? Something like that. Okay, now the second property we need here is just that the eigenvalues are non-negative, and this one's even easier. So if we take any lambda, which is an eigenvalue of our matrix, well, we can always assume that our eigenvectors have norm 1. So this is equal to lambda times 1, which is lambda x transpose x. Okay, so ax equals lambda x, right? So this is the same as x transpose ax. If we assume that our matrix is positive definite, then this is greater than 0. Or semi-definite, then it's greater than or equal to. Okay, so anyway, those are the easy parts of the spectral theorem. I'm going to skip over the hard part, which is showing that if I have a Hermitian matrix, then I have a complete orthogonal basis, meaning I can write Rn as basically the span of the eigenvectors of our matrix. And in fact, that even works in infinite dimensional spaces under some compactness assumption. Okay, so anyway, just a quick linear algebra warm-up for fun. Let's erase this real quick and move on. Okay, so in any event, that's enough linear algebra review for now. So now let's dive into defining the Laplace operator. So remember our progression. We're going to start with line segments, then n-dimensional regions, then graphs, and then finally surfaces and submanifolds of Rn. So let's get started. Now, to get started, we're going to motivate the Laplacian by kind of filling in that vibrational story, at least in one dimension. So here's how we can do it. We're going to assume that we have a set of n plus 1 particles that we're trying to simulate in some physics setting. So each of which is going to have mass, which we can call m, and it's going to be along an interval of length L. And what we're going to do is write down Newton's laws for simulating the vibration of these objects. So here's the basic setup. We're going to do, by the way, I always confuse it, I guess a transverse wave, is that right? The one that's vibrating horizontally. A string vibrates up and down, but that's technically kind of two-dimensional, so we're going to avoid that case. Okay, so in any event, here's our first particle, and it's attached by a spring to the second one, which is attached by a spring to the third one, and so on. And then finally, we have the last spring and another one. And we're going to denote a bunch of variables here, which are going to be written as u sub I. And the idea here is that u sub I is going to be the displacement from the rest pose of this object. So when I say rest pose, I mean like sort of the equilibrium setup here. So in particular, when the u's are equal to 0, the spacing of each of these guys is going to be the length of the total chain, right, which is the distance from here to here, divided by the number of particles, which we can call h. So h is kind of like spacing. Okay, so like when ui is 0, it's right in this position, which is like, I guess, equal to the number of springs in the chain multiplied by h. When ui is positive, it's displaced to the right. When ui is negative, it's displaced to the left. Okay? Now, we're going to make boundary conditions, namely that the endpoints of our spring system here are fixed. Right? They're not allowed to move. So they're just constantly equal to 0. And moreover, we're going to make the assumption that plus u is going to the right. And our task is to simulate the physics. So the other thing that we need is that k is going to be the spring constants. And our rest length for our spring, so in other words, the length that it wants to be, is going to be 0. So in other words, I kind of took a bunch of particles that were tied together by really tiny springs, and I stretched them out to an interval of length L, and there's n plus 1 particles total. So hopefully this basic physics setup makes sense. Okay, so as with almost every class in our department and many others, our life begins with F equals ma. Right, so the total force on each particle I here is equal to its mass times its acceleration. Okay, so in particular, this is equal to the mass, and we're going to do particle I. So this will be the second derivative ui divided by dt squared. Okay, and now we have to figure out what is the total force on particle I. And here when I say I, I'm going to assume that I is, I guess, between 1 and n minus 1. I'm not going to worry about those endpoints. Okay? Well, I've got two different springs that are yanking on particle I, right? One of them is on the left, and one of them is on the right. And both of them have rest length 0, and both of them have spring constant k. So let's do the one on the right. So what's going to go on the right? So here I've got k, and if you think about it, well, the force that I'm going to get in this case is just proportional to the kind of the distance between these 2 points, right? And that's because the rest length is equal to 0. And I just have to be a bit careful about the sign. What we'll find is that it's equal to k ui plus 1 minus ui. And if you kind of sanity check that really quick, that makes sense, right? Like if ui plus 1 goes really far to the right, yeah, then I would expect the force to be positive because this particle is going to want to move to the right. So that sanity check kind of makes sense. And similarly, I have a particle on the left. So what is that going to look like? It's going to look like k times ui minus 1 minus ui. Let's make sure that makes sense. So if ui minus 1 goes really, really far to the left, right, so it becomes negative, then f should become negative. So this ends up working out. Okay, and obviously I can rewrite this expression a tiny bit, right? This is k times, well, I've got k times ui plus 1, k times ui minus 1, like that. Okay, and then minus 2 times ui. Okay. So we can do a little bit of simulation here. And what we're going to end up with, let's say that we want to evaluate the total force on every particle. In fact, I'm even going to evaluate the force on the left and right-hand side particles. And I can do this in different ways. I can like try to balance it out or not. For now, I'm actually going to maybe ignore the fixed endpoint condition and pretend like they're free. We'll revisit that in a second. So in any event, okay, so what do I have? I have a 1, and a minus 2 as our coefficients here. So if I write all the u's in a vector, what am I going to get? I'm going to get that u double prime of t, right, that's like the second derivative, is equal to minus k times some matrix times u of t, where our matrix has a very nice structure to it, right? So again, I'm not going to worry about the first and last rows a whole lot. Maybe actually, you know what I can do for consistency? I'm only going to worry about the inner vertices. I'm just going to assume the first and last one are kind of fixed so that their double prime is equal to 0. In any event, what do I get? Well, oops, so there's no minus k because I'm just defining our matrix L. And what is our matrix L going to do? Well, I put a minus here. This is on purpose. I'm trying to suggest something we'll have in the future. But it has minus, I guess, plus 2's along the diagonal, and then minus 1's on the off diagonal. So it looks something like this. 2, minus 1, minus 1, 2, minus 1, minus 1, 2, minus 1. Here, if I'm not writing an entry, it just means it's 0. And then the second to last row, minus 2, 1, 2, minus 1, and then minus 1, 2. Incidentally, depending on your boundary conditions, this 2 might be a 1, but we're not going to worry about that a whole lot. Okay, so what did we just do? We showed that Newton's laws, up to boundary condition that I'm admittedly being sloppy about, look like u double prime equals minus k times L times u. Okay, and so this is kind of a nice, slick way to write this system. We'll see that it actually facilitates the way that we can solve the physics in practice. But for now, it's just kind of a nice form. And moreover, this is this nicely structured banded matrix. Now, let's kind of squint at this expression here. And let's think about that for a little bit. So one thing that we could do is like multiply both sides and divide by h and so on. And one thing that you might remember is that, like, if I have a function and it's sampled at a bunch of regularly spaced points, so in general, like I have a bunch of x's and I sample a function f of x at a bunch of points. If I want to approximate its second derivative, how do I do that? Well, one thing that I can do, so let's say this is h, right? And so this is maybe ui plus 1 and ui minus 1. And I'm now thinking of this as samples of some function on the interval from 0 to L. Well, then, you know, u d squared u dx squared, if this is the x-axis here, is roughly equal to what? Well, it's the difference in first derivatives, right? So it looks kind of like ui plus 1 minus ui over h minus ui minus ui minus 1 over h, all of this over h, right? This is some second derivative finite difference approximation. And of course, what do we see? Well, this is, you know, we can factor out all the 1 over h squared. And in the numerator, well, let's see, we have ui plus 1 plus, you see there's 2 minuses here, ui minus 1 minus 2 ui. And take a look. That, up to sine, looks an awful lot like what we've written here. So in particular, this operator L looks kind of like minus d squared over dx squared. And in fact, if we take a continuum limit of this sort of setup with a bunch of particles connected by springs of length 0, well, what we can get is simulating a continuum piece of string where every single point along that string can be associated with a tiny infinitesimal displacement. So in other words, we can take a limit to a function which we can think of as u of x comma t. And then the motion of our spring is determined by a partial differential equation, which looks like d squared u dt squared, right? That's like the second derivative here, is equal to, now I'm going to be super lazy here and say that there's just some positive constant, has to do with k and h and some other stuff, minus c squared times d squared u dx squared. Okay, so at the end of the day, oh, oops, I'm sorry. There's no minus the way that I've written it here, right? Because this second derivative and this matrix are differing by a sign, right? Okay. So what did we show? We showed that essentially, as we pass our spring system to a limit, the sort of continuum version of the spring simulation problem follows this partial derivative, or this partial differential equation, by the way, that you can write as PDE. which is essentially saying that like if u is uniformly 0, then my spring is just at rest. But now if I like grab a piece of the spring and I like pull it like that, and now the whole spring is kind of wobbling back and forth, then the displacements follow this function as a function of time, or this relationship as a function of time. As usual, you can see I've already managed to almost make a few sign mistakes, but I think that we're actually correct so far. So let's erase, clean up, and move on to the next slide in just a moment here. But to summarize again, we started with a bunch of particles linked into a chain, and we tried to simulate their displacement. And what we got was u double prime equals minus k, where k is the spring constant, L, which is a constant matrix with just 2's down the diagonal, negative 1's on the second band, times u. What we found is that minus L looks an awful lot up to a constant, like the second derivative operator. So really, this PDE, as I take the number of particles n to infinity, ends up looking like d squared u dt squared equals c squared d squared u dx squared. This is called the wave equation, and it's what governs things like vibration. So now we've finally, got to our vibrational formulas in one dimension. So let's pause and erase here. Okay, so here's where we're at so far. Essentially, by chaining together a bunch of one-dimensional springs and then waving our arms a little bit, we motivated a partial differential equation known as the wave equation, which is essentially simulating the propagation of a wave in a one-dimensional domain. Now, the wave that we motivated is kind of like taking a string and pulling it along the length of the string and letting go. Very similar derivation does it for pulling the string up and letting it go and letting it vibrate vertically. I kind of don't like that one as much because you have to make some trigonometric approximations to get to the wave equation where this one holds exactly. But in any event, essentially what the wave equation gives you is if I know the initial pose and velocity of this spring system or of this continuum sort of piece of rubber that's vibrating around, it tells me how to simulate it forward by giving the relationship between the time derivatives and the spatial derivatives. Now, moreover, although I already managed to confuse the sign almost, what we saw is that there's the minus second derivative operator appears in the wave equation as highlighted here. So we're going to think of our operators in today's lecture and in the next couple ones as acting on functions spatially. So here you see that u is a function of time and space, right? So space says, where am I along the piece of string? Like what part of the string am I looking at as it vibrates? And then t here is telling me, what time as time moves forward. So when I talk about operators, I'm going to say that they're applying to a function that's sort of fixed in time and just over the spatial degree of freedom, because that's what's going to matter for defining the shape analysis aspect, right? Our shapes are going to be static. In any event, it turns out that the really key operator and the thing that's sort of determining the dynamics in the wave equation is this operator that takes u and maps it to its second derivative, or minus its second derivative. Okay, and here we're going to give it this nice name. It's going to be a cursive L. So again, L is a linear operator that inputs functions and outputs their second derivatives. And if we have those pinned boundary conditions, then we'll say that L is an operator on this space. We're not going to worry about the weakest possible space. So we'll just say an operator on the space of infinitely differentiable functions on an interval from A to B with the condition that the functions are equal to 0 on the two endpoints. So like my vibrating string isn't allowed to vibrate out of place. So one thing we can do is actually kind of interpret L here as a positive semi-definite operator. And in fact, let's do that for both our discrete matrix L, right, like the one that we got by hooking together a bunch of particles, and our smooth operator L that takes functions and maps them to minus their second derivatives. So let's start with the matrix version. And then we'll do the smooth version after that. So I'm sorry that I accidentally erased L here. Remember that our matrix L looks like the following. So in particular, we had 2's down the diagonal, and we have minus 1's on the kind of off diagonal, like that. Okay. So now let's say that I have a vector u, And I'm trying to interpret L as a positive semi-definite matrix. So what I need to show is that U transpose times L times U is greater than or equal to 0. Okay, so what is this expression? Well, for one, it's the dot product between U and L times U. So let's write out that dot product. So it looks something like this. It is the sum over I of the ith component of U times, well, the ith component of LU. Okay, so I haven't done anything too exciting yet. But if we take a look at the form of our matrix here, by the way, I'm going to assume that like when I is out of range, like U sub minus 1, it's just 0. And that's going to be my lazy way of, rather than needing extra terms at the beginning and end of the sum, okay? So this is equal to the sum over I of Ui, and then reading off of our matrix, we're going to get a minus Ui minus 1 plus 2Ui minus Ui plus 1. And that's just based on the form of our matrix as we've written it here. And now we're just going to do some sneaky reindexing tricks. So first, I'll pull out this sum where we have a sum over Ui squared, right? So this is equal to 2 times the sum over I Ui squared. So we can put a little check mark here. And now, what do we see? This is essentially just Ui times Ui minus 1. And then we have a Ui times Ui plus 1. If we re-index the second one by shifting to the left one term in our sum, what do we get? Well, what we get is minus 2 times the sum over I of Ui times Ui minus 1. And this is where I is now going from kind of minus infinity to infinity, but we're just zeroing out any term that we don't have. Okay, so now we're in pretty good shape. In fact, actually, what we're going to do is kind of sneaky. We're going to take this 2 here, and we're going to write this sum in 2 different ways. So one of them is going to be the sum of Ui squared. The next one is going to be the sum of Ui, do I want to do plus 1 or minus 1? Minus 1 squared. So this is really equal to the sum over I of Ui squared plus the sum over I Ui. I keep looking at my notes because I can't decide whether to do minus 1 or plus 1. Minus 1 squared, like that. And essentially, all I did was just shift this sum by 1 index, which is perfectly fine. And then we have minus 2 times the sum over I, Ui minus 1. Well, why did I do that? Well, if I bring together all of these sums, we notice that this is equal to Ui minus 1 quantity squared. And this is greater than or equal to 0. Okay, so essentially what we showed, again, is that L is a positive semi-definite matrix, which is what we wanted to show. Now, remember that, so this is our finite dimensional case, and kind of in parallel with that, we can do the infinite dimensional version. So remember that cursive L takes a function u and then maps it to minus the second derivative. Oops, d squared u dx squared. And we can actually check a similar semi-definiteness condition for this one. So remember that the inner product of 2 functions, so we have u and L applied to u, is this equal to the integral. I guess in this case, we're dealing with functions on the interval from a to b. So it's the integral from a to b of u of x times L of u of x, which is the second derivative, right? So we have times minus d squared u dx squared, like that. Okay, and this is a function of x again. Well, if we integrate by parts, what are we going to get? So remember, integration by parts essentially moves one of the derivatives to the other term. So you get the boundary term, which is going to be du dx times minus du dx. So it's minus du dx, kind of all that squared, evaluated at a and b, and then minus what? Well, now minus the version. Oh, oops! I'm sorry. This is du dx times u. My apologies. It's actually not going to matter, and I'll tell you why in like t minus 3 seconds. Okay, minus the integral of the version where we move one derivative onto the other side, right? So we're going to get du dx like that, and then we get another du dx. Okay, but there's a minus here, so this is actually a plus. Okay, so I apologize. What I should have done is had a u here and not a du dx. But it doesn't matter because remember, the u is fixed at the endpoints, which means that this boundary term is actually equal to 0. What we're left with is the integral from a to b. This is the same thing twice, so this is du dx squared integrated over x. This is a positive number, so this whole inner product is greater than or equal to 0. So what did I show? With a little bit of confusion about the how to integrate by parts. Well, what we showed was how if we started with u and we worked with this minus second derivative operator, then the inner product between u and the operator applied to u always gives us a non-negative value. And that's because secretly what it's doing is computing this value here, which is like the integral of the square of the derivative. And this value is going to have a name. This is called the Dirichlet energy of our function u. And it's kind of, if you think about it, it's kind of measuring how wiggly u is, right? Like if u is a flat function, then a constant function, then du dx is equal to 0, and the Dirichlet energy is 0. If u has a lot of slope in it, then the Dirichlet energy increases. So what have we shown so far? We've shown that in our wave equation, right, we had a discrete wave equation which looks like u double prime equals minus k L u. And over here we had a smooth wave equation which looked like d squared u dt squared equals minus some constant times L of u. And in both cases we found that the operator L that's involved satisfies some kind of positive definiteness condition. So this looks kind of like a positive definite matrix, which is pretty nice. Okay, so let's erase and keep moving here. Okay, so far what we've shown is that we're dealing with operators that are in some sense positive semi-definite, right? When we have these inner product relationships like what I've shown on the right-hand side of our screen here and derived on the board. Now, in addition to this, somehow our operators are symmetric, they're positive semi-definite, and in fact that's enough to give them a set of eigenfunctions. So for example, the eigenfunctions of this operator L are what's shown on the screen here. Now, what do I mean by eigenfunction? Well, what I mean is that if I take minus the second derivative of phi k here, I'll get some constant of phi k, right? So in particular, let's say that I apply our operator L to one of our eigenfunctions, right? So I have L times phi k like that. Okay. Incidentally, notice that the phi k's all satisfy the boundary condition that I've put at the top here. Okay, so that's minus the second derivative. So what's going to happen? Every time I differentiate with respect to x, I'm going to get a factor of pi k over L that comes out, right? So I'll have the square root of 2 over L. That's just some constant. That's not going to matter. I'll have pi k over L squared, because I took two derivatives. Remember that the derivative of sine is minus cosine, like that. And then I just get this stuff on the inside, right? So it's sine of pi k x over L. Okay, so this is just minus the second derivative of this function phi k on the slide here. But okay, notice that this is equal to pi k over L squared times phi k of x. So I guess this is also a function of x. Okay, so what did I show? I showed that if I apply L to phi k, what I get back is phi k scaled by a constant. So what is this constant then? This is the eigenvalue, lambda k. And in fact, one thing that you can check is that these are orthonormal to one another. So namely, what we have is phi k inner product with phi L is equal to delta KL. This is just fancy notation for saying 1 if K is equal to L and 0 if K is not equal to L. The 1 is a byproduct of this carefully chosen constant 2 over L here. Oh, and I guess I've used L twice. So L is the length of the interval, so maybe I'll do K and M, like that. All right, so, right, and L here is equal to B minus A. Okay, so somehow we have similar story, right? So thanks to the spectral theorem, our matrix L for the discrete case has a complete set of orthogonal eigenvectors, whatever they are. Turns out they kind of look like sine and cosine, but we're not going to go into that into as much detail yet. And in the smooth case, we have a bunch of eigenfunctions, phi sub k, and actually thanks to Fourier series, one thing you might notice is that the phi k's actually span L2, right? I can write any square integrable function as a linear combination of these functions phi k, and they're sort of an orthonormal sequence. And so why is that powerful? What it allows us to do is to actually kind of solve the wave equation in some version of closed form. So here at the corner of the screen, I've given you the discrete and smooth wave equation, which we already kind of derived earlier. And one thing that we can do is use the eigenfunctions to solve this in a nice way. So let's do it in the discrete case first. So that's u double prime equals minus k L u. Okay, so again, this is the discrete wave equation, which I can write as u double prime equals minus k L u. Now, we've shown that L is a symmetric positive semi-definite matrix. So, by the spectral theorem, what do we know? Well, we know that there exist eigenvectors, and we'll call these, I don't know, what do I want to call my eigenvectors? I'll call them phi k. I guess these are in Rn plus 1. And eigenvalues, which we'll call lambda k, where the phi k's here are orthonormal and span Rn. Okay, so why is that important? Well, if I'm working in an orthonormal basis, what that means is that I can take u and I can actually write it in that basis. So u is a function of space and time, or in this case just time, right? Because I'm thinking of space as the slot of the different slots of the vector here. And I can write u as a bunch of coefficients, right? So in particular, I can think of u of t is really equal to a sum over k of the kth coefficient uk of t times phi k. So phi k here is fixed constant as a function of time because it's just some eigenvector of this constant matrix L, and the only thing that's changing is the coefficient in front of phi k. Okay, so we have this differential equation, u double prime equals minus k times L times u. So let's figure out what that means. So u double prime is really equal to uk double prime of t times phi k, all that summed over k. All right, so that's equal to, that's equal to uk double prime, or u double prime of t, just by definition, right? I took u and I wrote it in the phi k basis. Okay, so that's equal to minus k L times u of t, like that. And, well, we can expand out u of t again, so that's minus k L times the sum over k, uk of t times phi k. But we know that L times phi k is equal to lambda k times phi k. So in particular, of t times lambda k phi k. Incidentally, I'm noticing, once again, I've made a bit of a sloppy thing here. This k is the spring constant, and this k is the index in the sum. So I apologize for reusing a letter. Hopefully it's clear from context. My apologies. Okay, so let's read this from left to right. We have the sum over k of uk double prime of t times phi k is equal to some coefficient, oops, without the L because I'm accounting for that here, times the sum of uk lambda k phi k. So in particular, what this tells us is that uk double prime of t is equal to k, this is our spring constant k, times u k, this is the index k, I'm getting embarrassed by that, of t lambda, lambda k like that. Okay, so what did I just do here? Well, notice that this is the coefficient in front of phi k, and this is the coefficient in front of phi k, right? So we've got a minus k uk lambda k in front of phi k on the right-hand side, and we've got uk double prime in front of phi k on the left-hand side. This is an orthonormal basis, so we know that all the coefficients of our basis have to be the same. So we're now into an ordinary differential equation in just one variable, and this is solved by our choice of phi k up here. And so what do we get? Well, we essentially get a bunch of coefficients in front of the different phi k's for each of the uk's. What does that mean in more detail? So in particular, one thing you might recall from your undergrad ordinary differential equation class is that this is just an ordinary differential equation in time. I've eliminated space, so I can write uk of t is equal to some coefficient ak times sine of, let's see, it's going to turn out to be the square root of k lambda k. I'm so embarrassed. This is the spring constant, and that's the index times t plus bk cosine of the square root of k lambda t. I really don't like that. Maybe I'll underline all the spring constants just to be consistent. There's one like that. Okay. So I managed to talk a little bit in circles, but let's summarize what we did. We have a u here, and u is a vector, and it satisfies this ordinary differential equation, where my vector, as a function of time, the second derivative of that is equal to minus the spring constant times our matrix L times u, where L is just this constant matrix with 2's and minus 1's in it. Now, we showed that L is a symmetric positive semi-definite matrix, so the spectral theorem applies. And in particular, we have a bunch of eigenvectors and eigenvalues, where the eigenvectors are orthonormal, and the eigenvalues are greater than or equal to 0. So what does that mean? That means we can take u of t, and at each t, we can write it in the eigenvector basis, which is what we've done here, right? We've just written it as a sum over k of some unknown coefficient as a function of time times the basis. So now, on the right side here, we're just going to take our ODE, right? So our ODE is sitting here, right? This is u double prime equals minus the spring constant times L times u. We're going to plug in our basis. So what do we get? Well, we have uk double prime times phi k. And when we plug through it, we ended up with a lambda k times phi k. But these are two different expressions that are written in the same orthonormal basis, which means that their coefficients have to equal each other. So what does that mean? That means u double prime equals minus the spring constant times u times lambda. And this is just a one-dimensional equation without any x variable or anything else, right? This is an equation in one variable as a function of time. And by just undergrad ordinary differential equations, when we see this, we know that it can be written as some combination of sines and cosines. And I'll let you guys plug in the boundary conditions to figure out what the exact coefficients are. So the high-level takeaway here is that if I know the eigenvectors and eigenvalues of L, I can actually write the solution of our wave equation basically in closed form, right? So what's going to end up happening is at time 0, I can plug in my known value of u, and that's going to allow me to compute a and b here. I guess I need u and u prime. And now I just have some formula involving sines and cosines of how to simulate my vibrating object as it moves forward in time. Now, the really amazing thing here is if this sum were not just from k equals 1 to n, but 1 to infinity in the infinite dimensional case, then we would actually get exactly the same derivation. So it turns out that exactly the same kind of logic works for constructing solutions of the wave equation in the continuum case as well, which is laid out in the course notes. So 45 minutes later here, we can finally address our story. Can you hear the length of an interval? Well, the answer is unambiguously yes, because what are the vibration frequencies? Well, those are the eigenvalues of the Laplace operator, right? Because those are the sort of standing modes in this wave equation we just derived. And we derived that the eigenvalues are lambda k's. And notice that there's this 1 over L factor in lambda k, right? So what does that mean? That means as my string gets longer, the eigenvalues decrease towards 0. So if I give you the list of lambda k's, well, then I can actually tell you the length of the string, right? Just by, in fact, I only need 1 lambda k in the one-dimensional case. And it's just by inverting this formula. So you can hear the length of an interval. So finally, we can erase and move on to the higher dimensional case. Okay, so let's keep moving. So now our next task is to move from the one-dimensional case to the higher dimensional but flat case. We're going to talk about regions in Rn. And this is going to be sort of a reasonable next step in our discussion of Laplace operators. And we'll see that it's actually not all that different from the one-dimensional calculations I just fudged for the last hour here. So in particular, we're not going to derive the physics here, but the one-dimensional wave, or the n-dimensional wave equation is really not that much more complicated than the one-dimensional version. So here we're given a region. I'm going to do R2 just because I can draw it on the board, but you can think of the 2 as an n, really nothing changes. And we're going to assume that the boundary of our region is some connected, smooth object. Then the wave equation is the partial differential equation that I've written at the top of the slide here, which is that the second derivative of u in time. Remember that I'm thinking of u as a function of both position and time, right? So I have a wave that's propagating, and here maybe position is like the displacement, and probably vertically now in the higher dimensional case, and time is time. Then the Laplacian is this minus the sum of second derivatives over all indices I, and the wave equation is given by the second derivative of u in time is equal to minus the Laplacian of u. So this is the equation that governs waves as they move around on drum heads. So now our boundary condition probably is that u is equal to 0 along the entire boundary of omega here. Now, our Laplace operator, this delta object, there are many different ways to define it. A very typical piece of notation is that the Laplacian is equal to the divergence of the gradient. And indeed, that makes sense, I guess, minus the divergence of the gradient. So in particular, if we think of the gradient operator as like a vector of d over dx1, d over dx2, and so on, then the dot product is like the sum of second derivatives. So that's really where this notation is coming from. Now, one thing you might notice, which is kind of weird, is that this Laplace operator, right, the way that we've written it, so again, we've written that the Laplace operator may be applied to a function u is equal to minus the sum over I of the second derivatives of u in space. Again, not in time. We're not going to do that. Like that. Somehow that feels very coordinate dependent, right? Like this is summing over, you know, the x direction, the y direction, the z direction, whatever, one by one. But that doesn't really jive with our understanding of physics, right? Like if I take a drum and I rotate it 30 degrees, I wouldn't expect my drum to sound different. That would be a very different universe. But this form of the Laplacian sort of depends very carefully on the set of axes that I've chosen to do my computation in, which isn't great. So here's one useful property, which is that the Laplacian is an intrinsic operator. Essentially what that's going to mean is that if I rotate my domain and my function along with it, then the Laplacian doesn't change as long as I account for the changing coordinates that just happen. So in particular, let's do this in a little bit more detail just for fun. So here we're going to define two different functions. I've got one function f of x, which is just some arbitrary function which is smooth on our domain here. And I've got another function g of x, which is going to equal f of rx plus t, where we're going to think of R as some orthogonal matrix, and t is like a translation vector. So essentially f and g are the same function, just up to rotation and translation. And in particular, we're going to call the variable y is equal to rx plus t. And essentially what I want to show is that the Laplacian in the y coordinates is equal to the Laplacian in the x coordinates. So like nothing interesting happens even though I rotate it, so long as the corresponding points are the same. So for instance, if I have a function on the square and now I rotate the square 45 degrees and my point here ended up there, then the Laplacian of my function evaluated at this point equals the Laplacian of the rotated function evaluated at that point, which by the way is not obvious the way I've written it here, right? Because this is a sum over coordinates, and the coordinates here changed, assuming that x and y are still the same. Okay, so let's just do that calculation real quick. So in particular, by the chain rule, what do we know? We know we can write an alternative form for the gradient operator. So we have d over dxi, but what do we know? We know that we can write we can follow the chain rule and say that this is equal to the sum over j of the following. Well, it's going to be dyj of dxi like that. Is that right? Times d over dyj. Yeah. This is just the chain rule, okay? And of course, this is the same as the sum rji d over dyj. Okay, so all I've done right now is just change of coordinates. Nothing too exciting, but okay. So let's think about this. What does this mean? This means that somehow our gradient operator, which is just a vector of these things, we'll say maybe gradient in x, is equal to, well, this is kind of like R transpose times the gradient in y in formal notation. Okay, so what does this mean? Well, remember that Laplacian in x. Let's see if I can do this in kind of formal notation. The course notes does it more carefully, but of course this is really equal to what? We can think of this as the gradient in x transpose, if we think of this like a vector, times, times the gradient in x, sorry. Oh no. So there's a gradient in x transpose times the gradient in x, right? And this is the div of grad, right? So it's like the dot product between this vector of partial derivatives in itself, which is equal to gradient. Okay, so we have gradient x is equal to gradient of y times r transpose. So okay, this is the gradient y transpose r transpose the gradient in y. This is just equal to the identity. So we see that this is equal to the Laplacian in y. Now this is kind of a sloppy derivation, but I think the high-level point here is that really, if you think of the gradient as just sort of a vector of these partial derivative operators, well, translation obviously doesn't do anything. So we don't have to worry about that when it comes to derivatives. For rotations, well, we rotate our coordinates, so that ends up basically taking this vector and multiplying it by r. But okay, if we dot product the gradient with itself to get Laplace operator, guess this is minus the Laplace operator, technically, then, well, we end up with rotation transpose times itself, which just goes away. So that's essentially the basic point here, which is to say that, again, our Laplace operator is coordinate independent. Like if I rotate my domain and my function with it, like the colors here, essentially when I apply Laplacians, that sort of commutes with this operation. All right, so far we've shown that at least physics is coordinate independent, which is a good thing, right? If we rotate a drum, somehow its vibration, frequencies, and patterns don't change. They just rotate along with the drum. But now I want to give you another intuition for the same operator, so we don't have to just think about the wave equation. In fact, there's so many different ways to think about the Laplace operator that we're going to try and introduce as many of them as we can in the next couple lectures. Now, another way to think about the Laplace operator is that it's a really instrumental piece of a tool for measuring how smooth a function is. Now, I already mentioned this term earlier in the lecture, but it blew past a little bit quickly, so let's do it in a bit more detail now. In particular, let's define an object called the Dirichlet energy, I don't know, don't speak French, of a function u. So u assigns a value to every point in a domain. So for instance, in these pictures here, we have two different functions. I'm sorry, those are labeled f instead of u, but whatever. And the color is being used to denote the value of our function. And the function on the left is sort of non-smooth. Now, I mean this in an informal fashion, just that it like wiggles up and down a lot. I don't mean it in the like C infinity sense. Whereas the function on the right is somehow much more smooth, right? Like it doesn't have so much oscillation, it's just filling in the boundary data in a much more kind of direct way. So this Dirichlet energy, essentially, what is it doing? Well, let's take a look. So it's defined on the top of the slide to be the integral of the norm of the gradient of u squared, integrated over our domain omega. So again, u is a function. So its gradient is telling us the rate of change of u. For example, if u is constant, then the gradient is 0. So if u is wiggling up and down wildly, then its derivative is going to become quite large, right? Because it has to be the slope of all of these oscillations. And correspondingly, the Dirichlet energy, like of the function on the left-hand side, is quite big. On the right-hand side, the Dirichlet energy is relatively small. So the Dirichlet energy measures something about the total amount of first derivative hiding inside of a function in a domain. And it turns out that the Dirichlet energy also gives us some way of motivating the Laplace operator. In particular, on the right-hand part of this slide here, I give you an optimization problem. Here's the problem. I'm going to prescribe the values of u along the boundary of a domain. So for instance, in this weird shape here that my colleague Etienne has drawn, I know the color, like the red and the blue values of the function, just along the boundary of the shape. And I want to solve an interpolation problem, which gives me the values of u everywhere else in the interior of the domain. So the way that I'm going to do that is by finding the smoothest possible function u. In other words, the function that satisfies this Dirichlet, that minimizes the Dirichlet energy while satisfying my boundary constraints. And that gives me this optimization problem I've given you on the right-hand side, right? Minimize e of u subject to u prescribed on the boundary. So again, I can think of this, if I expand out my formulas a bit, as I want to minimize 1/2 times the integral over omega, the value of the gradient of u of x squared integrated over omega, over all possible functions u that satisfy that u restricted to the boundary of our domain is prescribed. Okay. Now, given our approach in the last n lectures for large N, what do you think we're going to do? We're going to compute a variational derivative to solve this problem. In particular, here's how it's going to go. Let's actually derive that essentially what that's going to imply is that the Laplacian of u is identically equal to 0 in the interior of a domain. Okay, and in fact, the Laplacian, we'll see, actually shows up in measuring the Dirichlet energy as well. So here's how we can do it. Let's give ourselves some space. So the first thing that I'm going to do is just write an alternative expression for the Dirichlet energy. So remember, we've got the Dirichlet energy of some function u is equal to 1/2 the integral over omega of the norm of the gradient of u squared dA. And of course, norm squared is nothing more than the dot product of a vector and itself, like that. Okay. So now what are we going to do? Well, we're going to crack open our multivariable calculus textbooks again. Essentially, whenever we see the integral of like the derivative of something multiplied by something else, this should be screaming out in your mind. You should be like staying up late at night thinking, I should be integrating by parts in this function. And indeed, that's absolutely the case here. I need to integrate by parts the expression that I see here. And roughly, integration by parts, you can look at the Wikipedia page for multivariable integration by parts, or go back to your multivariable calculus class. Or you can just remember that multivariable integration by parts kind of says, if I have two derivatives multiplied together, this is equal to some boundary term minus something where I move derivative to the other guy. That's basically it. So what am I going to get? I'll get some boundary term, which I'll write, as ... dl for boundary. And now we'll have minus something else. So in particular, what are we going to get? Well, we'd move our derivative here. So this is going to be 1/2 the integral, the div of the gradient of u of x multiplied by u of x, because we moved the derivative off of that second term, dA. But aha, we have a minus div of grad, so this is nothing more than boundary terms, right? That's this ... that I've written here, plus the integral over omega scaled by 1/2 of u of x times the Laplacian of u at x dA. Or, a fancy way to write this is that this is the inner product of u and Laplacian u. Okay. So what is this telling us? It's telling us that the Dirichlet energy of our function u, if we ignore terms that are on the boundary, which is sort of okay here because the values on the boundary are prescribed right now, then this is really equal to the inner product of u and its Laplacian. Now, just to make our story even more complete, let's show that if we actually want to solve this optimization problem, we end up with the linear condition that Laplacian u equals 0. So how are we going to do that? Well, it should be screaming out to you guys to take the variational derivative, which we actually already did in lecture 2, but let's review how we could do that. So in particular, here's our domain omega. Oh no. Here's our domain omega. And we have some function u, which is mapping this to the real number. And we know the value on the boundary. So now we're going to take a second function. And let's say it's, I don't know, what's our favorite value? Let's say w, which also maps omega to the real numbers. Okay, so just some second function. And we're going to think of this as our perturbation. Remember, our basic goal in variational calculus is to say if we minimize some functional, then perturbations are going to give a 0 derivative, right? Hopefully that phrase is starting to make sense as we practice it more in this course. But we're going to say, well, we're going to assume that u is optimal. And we want to learn something about u. So what does that mean that u is optimal? It means that u satisfies our boundary constraints. And we don't want to mess that up when we perturb it by adding some function w. So what we're going to do is we're going to assume that w restricted to the boundary of our domain is just identically equal to 0. Okay, so that way, what do we know? Well, we know that u plus hw now satisfies our boundary condition for any scalar h, right? Because essentially, we're just not messing with the values on the boundary. So what are we going to do? Well, as always, we'll compute the Dirichlet energy of u plus hw, right? This is some function on our domain omega, right? So when h is equal to 0, it's our function u. And as h increases, it's some perturbation of our function u. And what do we know? Well, we know if u is optimal, then we can compute the derivative of this with respect to h at h equals 0, and I should get 0. Why is that? Well, again, as a bit of review of our variational calculus style reasoning here, right, we have some plot like this, where h is a scalar, and our vertical axis is Dirichlet energy of u plus hw. And notice for all h, u plus hw satisfies our boundary condition because we constructed w to make that happen. Okay, so if u is optimal, then essentially the Dirichlet energy of u is the lowest possible value you could get. So like that is some point here. And now as I increase h, or decrease h, well, no matter what, the input to the Dirichlet energy is going to be some other function that isn't u. So necessarily, it must increase. Might not be monotonic, it might wobble around like that, but we at least have a local optimum at this point. And that's what this expression is telling us. And so now let's fill in what that expression means in a little bit more detail. So what am I going to get? I'll get that 0 is equal to d over dh of our Dirichlet energy evaluated at h equals 0. Okay, and what is our Dirichlet energy? Well, I'm going to actually skip the boundary term here, and I know that that's safe because the boundary term is not a function of h, right? Because w is equal to 0 on the boundary. So this term is just going to be constant as h varies around. So actually, the only thing that matters is this guy here, right? So it's actually equal to d over dh of 1/2 the integral over omega of u plus hw times the Laplacian of u plus hw, where the Laplacian is in the x-coordinates, so it's not an h, dA. All right, and this whole thing, oops, so that should be a plus because I've borrowed this expression here. And this is evaluated at h equals 0. Okay, so what's going to happen when we differentiate? Let's actually work this out. So if we apply the product rule, well, what are we going to get? We'll get 1/2 the integral. We're going to pass the derivative over h into the inside of the integral here. So this is differentiating under the integral sign. So by the product rule, that's equal to the derivative of the first term times the second. So here, the derivative with respect to h of u plus hw is just w times the second one, which is going to be Laplacian of u plus hw. But here h is equal to 0, so we're just going to get u. Plus, okay, so now we have to do our product rule the other way. So we're going to get u plus hw evaluated at h equals 0. So that's just u times Laplacian of this thing, derivative with respect to h. So that's w, like that, dA. Now, if you look back earlier in this lecture, one thing you can do is integrate by parts here 2 times, and you'll get irrelevant boundary terms plus essentially moving the Laplacian onto the other object, right? So if I integrate by parts once, I'll get, the gradient of u times the gradient of w. In fact, maybe we even assume that, the gradient of w is 0 on the boundary, just for ease of math. And then if we integrate by parts a second time, well, now we're going to get Laplacian of u times w. So in fact, these two terms are the same. So what we get is that this is equal to the integral over omega w Laplacian of u dA. And so now let's stare at this expression here. What did we show? We showed that for any w that satisfies that w is equal to 0 on the boundary of our domain, we get that 0 is equal to the integral of w against Laplacian u. So this is true, again, for all w with w restricted to the boundary of our domain identically equal to 0, which is a really strong condition, right? So we're sort of like testing delta u here against different choices of w, and no matter what we multiply it by, we get 0. So what does that tell us? This is kind of like saying, like, I have a number, and no matter what other number I multiply it by, I get 0. So necessarily, this thing is actually equal to 0. So what we can conclude, just like we have in many other derivations in this course, is that the Laplacian of u is identically equal to 0 in the interior of the domain. Okay. So if we step back 10 feet, what did we just derive here? What we essentially just showed is that if we start with this optimization problem, we want to minimize the total gradient of our function u over all possible functions u whose value is known on the boundary of our region omega here. Then, well, the first thing we did was show an alternative formula for Dirichlet energy, essentially that it's equal to some integral along the boundary, which I've been lazy about because our boundary information here is fixed, plus the inner product of u and its Laplacian, up to 1/2 scale here. And when we took the variational derivative, I mean, this is kind of like u transpose Lu, so unsurprisingly, we just get Lu as the variational derivative. And indeed, essentially, what our variational calculus argument shows here is that necessarily, if u is optimal for this problem, its Laplacian is identically equal to 0 in the inside of omega. So this kind of a function that satisfies this condition, plus, remember that u on the boundary of omega is prescribed. This has a name. This is called a harmonic function. A lot of kind of audio terms show up in this literature here. So a harmonic function satisfies this condition that it has 0 Laplacian. And we'll see that there's a lot of really nice geometric conditions that are associated to harmonic functions. So let's pause for a moment and erase, and then we'll continue here. Okay, so let's take a look at some examples of harmonic functions. These were rendered by my colleague Etienne Vuga at UT Austin. So remember, the harmonic equation says that the Laplacian of a function is identically equal to 0 on the interior of a domain, and that on the boundary of the domain, the value is prescribed. So in this little schematic here, essentially we can think of these shapes as like somebody pinned down the values of our function, which are like heights over the plane, along the boundaries, like the outer loop, or maybe the outer loop plus the inner loop in this toroidal example, and then solved this harmonic equation to interpolate those boundary heights to the interior of the domain, and you get these interesting looking functions like what are shown in here. And the harmonic functions satisfy all kinds of super nice properties, right? They interpolate the boundary data in a nice smooth fashion. They also satisfy something called the mean value property, meaning that it's actually kind of interesting. It says that if I choose a point in the interior of the domain, and I draw a little circle around that point, which is contained strictly within the interior of the domain, the value at the center is actually equal to the average of the value of your function in that little disk. It's kind of incredible that you can achieve this property in some sense. What it's saying is that every point is equal to kind of the average of its neighbors, and we'll see that that's actually sort of a jumping off point for constructing discrete Laplace operators later. In fact, harmonic functions have all kinds of nice properties and applications. One of them is in cage-based deformation. So this was one of the sort of primary techniques that was used in computer animation for a while. For example, I think this paper was a technical report from Pixar Animation Studios, where I draw some volumetric cage around a character that I'm trying to move around. So you can see this 3D character like this boy here, and then there's a cage, which is this coarse set of black polygons on the outside. And essentially what harmonic functions allow you to do is to write the position of every point in the interior of the cage as a linear combination of the boundary points. So then when I deform the outer cage, which is easy to do as an artist because it has relatively few points, I can use those same harmonic coordinates, which are basically just solutions of the equation that we just wrote down, to take the 3D character with it. So this is like a nice, very simple way to get elastic-looking deformation of a shape that's artist controllable. I'll let you guys do a little bit of reading on this particular application of Laplace operator. This work is also making use of the fact that you actually can write a closed form solution to that Laplace equation, that delta f equals 0, when your spaces are 3, which is something that we won't cover for now. So anyway, returning to this Laplace operator, right, this thing that takes a function and maps it to the sum of its second derivatives, we can see that it satisfies a lot of conditions that are similar to the ones that we checked in the one-dimensional case. So here, if we look at the space of functions f, which are identically equal to 0 on the boundary of our domain omega, then we can think of Laplacian as sort of operating on that function space. It actually might not output functions in that space now that I think about it, because like it might add boundary information. I have to think about that a little. But in any event, if we at least think of our input to the Laplacian as functions in this space, we can see that it's positive and it's self-adjoint. So remember that positive is sort of like our analog of being a positive definite matrix. And self-adjoint is kind of like our analog of being a symmetric matrix. So let's actually show that. So in particular, remember that we're going to now assume that our function f is identically 0 on the boundary of a domain. And maybe that it's all of its derivatives are 0 also. Like maybe we even just inset our function f from the boundary a little bit to just avoid boundary terms altogether. Okay, so let's take a look at the inner product of f and our operator applied to f, like that. Okay, so what is this thing? Well, it's the integral on omega of f of x times minus div of grad of f of x dA. And just the same as we derived the Dirichlet energy, if we integrate by parts, well, we're going to get a boundary term. But remember, f is identically equal to 0 on the boundary, so that boundary term is 0. So actually what we get is just minus times that other minus, so that becomes a plus, the integral of the gradient of f, right? So we're moving this divergence here, evaluated at x, dot producted it with itself, so that's just the 2 norm squared dA, which is, of course, greater than or equal to 0. Okay, so our operator is positive. And moreover, it's symmetric in the sense that if I integrate by parts twice, what I'm going to get is essentially moving the Laplacian from one term to the other. So let's start doing that calculation and see if we get to the end without making a mistake. So we have f times the Laplacian of g. So once again, that's equal to the integral in our domain omega of f of x times minus div of grad of g of x dA. Okay, well, let's see here. So we're going to get boundary terms, but there aren't boundary terms because f is 0 on the boundary, minus, but the minus becomes a plus. So this is really equal to the integral along omega of gradient of f of x dot product gradient of g of x dA. Okay, so this is again just integrating by parts. But okay, so this thing is symmetric in f and g, so we can kind of follow the same argument backward. And what we get is just that this is g times Laplacian of f. Okay, so we have a symmetric and positive semi-definite style operator, which means that it, in some sense, is going to satisfy a version of the spectral theorem. Like it has eigenfunctions and eigenvalues, and the eigenfunctions actually span L2 for the appropriate function space. Let's erase and see what that looks like. Okay, so right, so now let's take a look at what these Laplacian eigenfunctions look like. So here I'm showing you a few for a given region. These are what we call Dirichlet eigenfunctions, meaning that I've added a constraint that u here is identically equal to 0 on the boundary of our domain. One thing that you can check is that the eigenfunctions, so the functions that satisfy like Laplacian of u equals lambda times u, actually are critical points of the optimization problem that I've written on the slide here, where I'm now minimizing the Dirichlet energy, but I'm adding a constraint that our function u has to square integrate to 1. So maybe we'll actually, yeah, I'm going to let you guys figure out at home why if I start with this minimization problem, then what I'm going to end up with is the following, just Laplacian of u equals lambda times u, where essentially I start with this optimization problem here, and the lambda is going to be the Lagrange multiplier for the constraint that u square integrates to 1. Now, one thing to ask is, why do we need this constraint that u square integrates to 1? Well, otherwise, the obvious minimizer of the Dirichlet energy would just be 0, right? The function that's identically 0 is extremely smooth. It satisfies our boundary condition, but it's also not super interesting. So the way that we get around that is by making it square integrate to 1. And in fact, we can look at a whole sequence of eigenvalues of our Laplace operator, each of which comes with an eigenfunction that satisfies this relationship. And one thing that we'll see is that actually the eigenvalue here, this is actually equal to the Dirichlet energy, right? Because remember that Dirichlet energy is roughly just u times the Laplacian of u. But here, the Laplacian of u is lambda u, right? So this is actually equal to the Dirichlet energy of our eigenfunction u. So what does that mean? That means that if we compute the vibration modes of our Laplacian, right? Remember that vibration modes are functions that satisfy this relationship here. And we look at the vibration frequencies, which are the lambdas, then essentially the modes are organized by increasing Dirichlet energy. And that makes sense, right? So think about like eigenfunctions on the interval, right? So maybe you have a flat function, and this one will be discounted as uninteresting if we have this square integral condition. Then the next eigenfunction would be like 1 lobe of sine. The next eigenfunction might be 2. I'm going to have trouble drawing the next one, which is 1, 2, 3, something like that, and so on. And these obviously this is lambda equal to 0, it's just a constant function, lambda equal to whatever. But this is lambda 1, lambda 2, lambda 3, and as we look at increasing eigenvalues of our Laplace operator, the corresponding eigenfunctions get more wiggly, and now we can see that that actually makes sense, right? Because essentially it corresponds to higher Dirichlet energy, which is exactly the same as higher eigenvalue by this little derivation here. Now, one thing that we can do is look at the whole sequence of eigenvalues. So there's actually infinitely many of them when you have a region like this. So in other words, there's a bunch of pairs like lambda k, uk with the constraint that, Laplacian of uk equals lambda k times uk, like that. And we can sort them by increasing lambda. What we'll see is the lambdas go off to infinity, but they go off to infinity in a different pattern for every shape, right? Because these lambdas here are basically a function of the shape of the boundary of our domain. But that said, already what we'll find is that there's interesting geometric information that's hiding in the Laplacian spectrum, right? This is another toehold into that can you hear the shape of a drum question. So there's a really famous theorem, we're not going to prove it in this course, called Weil's law. which looks at the number of eigenvalues of a Laplace operator for a shape where the function n of lambda is like the number of eigenvalues that are less than or equal to lambda. And one thing you can do is show that the rate at which n goes off to infinity as a function of lambda has to do with the dimensionality of your domain, as well as the volume and some nice constant. And so essentially, what is this saying? It's saying that you can sense dimensionality by looking at the sequence of Laplacian eigenvalues. So if I give you an interesting puzzle, like here's an infinite sequence of lambdas, you tell me was my region in R1, R2, R3, or whatever, I could do so by computing the limit that's given in Weil's theorem and kind of figuring out the rate at which things are diverging or converging. So anyway, that sort of concludes our main discussion of one-dimensional data. Incidentally, I did mention that we can use Laplacian as a way to interpolate, right? Like you can think of harmonic functions as an interpolation tool, right? I took data on the boundary and then I saw Laplacian f equals 0 to interpolate that boundary data to the interior. But I should note that that's not always a good thing to do. So one thing you might have noticed about the pictures that we're drawing is that they look an awful lot like tent poles. And that's absolutely right. The Laplace equals 0 is somehow simulating like a very thin rubber sheet where I've pinned the value of a function at a few points. But as an interpolant, that's probably ill-advised, right? Because, like for example, here, if I'm interpolating between, the height of the boundary of the tent and like the points, like what you're seeing in this picture here, then your function ends up with kind of singularities at all the points p, which is probably not great. Usually we look for smooth interpolants of our data, right? So like if I have some function on a region omega and I know the values of the functions at a few points. So one problem in computer graphics where this is the case is called skinning. All right, one thing I could do would be say, oh, okay, like if I know the value of my function at a few points, and maybe also along the boundary of my domain, then I can interpolate it everywhere else by solving, Laplacian of f equals 0 on the inside, subject to those boundary constraints. But it turns out that what you'll end up getting is a function that sort of has discontinuous derivatives at these points where you've constrained the value. And in fact, in higher dimensional domains, even two-dimensional domains, I think this problem may not even be well posed. So this is just a common misconception, and sometimes this artifact, this like pointy thing where you're interpolating your data but you're getting a derivative singularity, is called loss of ellipticity. The basic idea here being that Laplacian equals 0 is what's known as an elliptic partial differential equation. Ellipticity usually guarantees smoothness, but somehow we violated the assumptions that are needed for smoothness in this particular case. Okay, so remember we started by defining Laplacian in one dimension as the thing that takes a function and maps it to minus its second derivative. Now, in higher dimensions, but still regions in Rn, we define the Laplacian to be the thing that takes a function and maps it to minus its sum of second derivatives. And we've shown that it satisfies a lot of similar properties. It's symmetric and kind of positive semi-definite. It's linked to the wave equation and also this measure of function smoothness called the Dirichlet Energy. Now we're going to do our first discrete example, and we're going to talk about Laplacians on graphs, like just collections of vertices and edges. So let's clean up the board a little bit and then continue. Okay, so hopefully you guys are seeing the pattern in this lecture so far. The Laplace operator, or this thing that looks like minus the sum of second derivatives, shows up all over the place, and it always has kind of similar properties. It has something to do with measuring smoothness, like the Dirichlet energy. It also is involved with the wave equation. So our first two examples here are combinatorial in nature. Now we're going to move on to, our first two examples are continuum in nature. Now we're going to move on to a combinatorial example. Namely, we're going to talk about Laplace operator on graphs. My basic goal in our lectures here, introducing Laplace operator, is, in some sense to build up a lot of intuition and redundancy between a lot of related stories. This way, when I screw up the math on one story, maybe I can make up for it in the next one. Okay, so here's going to be our basic setup. So remember that a graph is a collection of nodes that are connected together by a collection of edges. So when I talk about a function on a graph, whereas like when we talk about a function on a surface, it's like a value at every point on the surface. Here, when I talk about a function on a graph, what I mean is an assignment of one value to every vertex of our graph. And here's going to be the way that we'll construct a Laplace operator on a graph, which is to measure the Dirichlet energy of a function on a graph. Right? So again, maybe I have some graph domain, like I think what was on the previous slide was this graph here. Happens to be a tree, but that doesn't really matter. And now at every vertex, I assign some value. Maybe this one's 7, and this one's 10, and this one's 11, and this one's 13, and this one's, 4, and this one's 2. Now the question is, can I measure the smoothness of my function on my graph? So I have an assignment of a value to every vertex here. Is this a smooth assignment? And in particular, what we're going to try and do is construct some analog of Dirichlet energy with very similar properties. So for example, if my function is constant, like just the same value at every vertex here, then the Dirichlet energy is going to be 0. And here's the way that we're going to do it. So remember that the Dirichlet energy of a function on like Rn I got by computing the gradient and then integrating its squared norm. I can do something very similar here, where I can subtract values of our function along every edge of our graph and then look at the sum of squares of those differences. So for example, like we have 11 minus 7, which is 4. We have 10 minus 11, so maybe I get a -1 here. 13 minus 11 is 2. I'll be embarrassed when I find the mistakes later. 2 minus 13 is minus 11, and then 13 minus 4 is 9. Right, so those are the differences of our function values along every edge. And now our Dirichlet energy of this function on our graph is just going to be the squared sum of all these values. So like 4 squared plus minus 1 squared plus 2 squared plus minus 11 squared plus 9 squared. So that's it. Hopefully you guys see what the Dirichlet energy that I'm proposing is going to do. It takes a function on a graph, which is just a value assigned to every vertex, and along every edge, it looks at the difference in values at the two endpoints of the edge, subtracts the two, and then squares. So like the 4 is 7 minus 11, or I guess 11 minus 7, and then I square, and so that's what I'm going to get here. So now we're going to work out that formula in more generality. Okay, so for our more general construction, what we're going to do is first define a matrix that I'll call a differencing operator. And the differencing operator is an edges by vertices matrix with entries that are either -1, 0, or 1. So essentially what I'm going to do is I'm just going to make the differencing operator, every row of our matrix is going to correspond to a different edge. And it's going to put a +1 on one end of the edge and a -1 on the other end. We're going to just arbitrarily orient our edges. Remember that at the end of the day, we sum the squared differences, so it kind of doesn't matter which end of our edge is the head and which one is the tail. Okay, so if I think of a function on my graph as a vector in RV, well, then d times our function is going to be a vector in RE, which just gives the difference along every edge. So that would be kind of like going from the white values inside of the circles here to the black values along all the edges, right? That's what D is. It's just that mapping. Okay, so if I wanted to find the Dirichlet energy, just like we did on the board here, well, essentially, I can write it in two different ways. Remember that df is nothing more than the differences in the values of f along every edge. So if I take the squared norm of that, then I'm going to get exactly that Dirichlet energy like what we wrote down just a few moments ago. Or if I expand the norm of df squared, I get this sum on the right-hand side, which is the sum over all edges of the difference between f on one end of the edge and f on the other end of the edge. So this is the norm of df squared. Okay, so if we operate kind of an analogy to our discussion of the relationship between Dirichlet energy and Laplace operator, then here's how we can get a Laplacian operator on a graph. It's quite simple. It's just d transpose times d. And how do I get that? Well, I'm going to start with the Dirichlet energy. If we look at the top of the slide here, that's equal to df norm squared by definition. Now remember that the norm of a vector is the same as the transpose of that vector times itself. And so that gives me f transpose times d transpose d times f. So if I group that the other way, I get the dot product between f and d transpose d times f. So that quantity is what we're going to call the Laplacian applied to f. And essentially we're going to define L to be d transpose d. Now, once again here, I've unfortunately overloaded my notation a tiny bit. So maybe I'll actually fix that really quick. Okay, so I sneakily put a little bar over the, the d in this blue equation to avoid overlapping with the other matrix d on the top of this slide. But essentially, this Laplace matrix L, I can write in two different ways. I can write it as d transpose d, like the top of the slide. Or I can write it as the adjacency matrix of my graph minus a diagonal matrix of vertex degrees, which I'll call d bar. And it's very easy to see that our Laplacian matrix L is symmetric and positive definite. It's symmetric because it's equal to d transpose d, which is a symmetric expression. And it's positive definite because, well, when I do like f transpose LF, I'm secretly computing Dirichlet energy, which is non-negative. And so this is the graph theory analog of our construction of the Laplace matrix, which is pretty nice. And it allows us to do a lot of calculations that are similar to what we've done in continuum case, but on a graph as well. One thing you can check, incidentally, if you go all the way back to when we derived the Laplacian of a set of particles connected by springs, is that the Laplacian matrix for that set of particles was exactly this, where our graph was the line graph. Now, one question you could ask is, what is the smallest eigenvalue of the graph Laplacian? And if we think about it for just a minute, remember, again, it's equal to d transpose d. So if I have a vector 1, 1, 1, 1, 1, 1, 1, 1, well, d times that vector is going to be 0, which means that the smallest eigenvalue of graph Laplacian is just equal to 0, which isn't terribly exciting. But the second smallest eigenvector and eigenvalue become interesting. So for example, here I'm showing you the second smallest eigenvector, or really this is the eigenvector corresponding to the second smallest eigenvalue. And this object is called the Fiedler vector, or the algebraic connectivity of your graph. It's a super interesting function. It doesn't have local optima kind of in the interior of your graph. It kind of is the smoothest possible interesting function on your graph, like you can see here. And it's actually used quite often for graph partitioning. So we'll see much later in this course when we talk about clustering and segmentation that actually if we compute this eigenvector and then just cluster out the negative, the vertices where x is negative from the vertices where x is positive, this actually gives us a reasonable clustering our graph. Like for instance, for this barbell graph, it'll separate out the left cluster from the right, which is pretty cool. Now, there are all kinds of nice properties associated to graph Laplacians as well. So for example, that mean value property that we kind of drew a picture of for the Laplacian in Rn also works out on graphs. In fact, it's quite easy. So if I have a function per vertex with the relationship that L, like our graph Laplacian times our per vertex function is equal to 0. Okay, well remember that our graph Laplacian is just equal to this matrix, which is the adjacency matrix minus the degree down the diagonal. So one thing you can see is that if graph Laplacian of some function is equal to 0 at a vertex, then it actually satisfies the mean value property, namely that the value at that vertex is equal to the average of the values along its neighbors. This is useful, for example, for surface parametrization. So this idea of defining a Laplace operator on graphs turns out to be the tip of a really beautiful mathematical iceberg. And this is an area of mathematics called spectral graph theory. Here I'm including in the slides a pointer to a really nice textbook in this area that steps through a lot of the basic results in this field in a very clear fashion. spectral graph theory is really cool. Essentially what it's doing is walking through the theory of partial differential equations and spectral geometry and making it work on a discrete structure like a graph. And one of the really interesting observations in this area of math is that constructions that used to tell us something about geometry in the spectral graph theory case tell us something about combinatorics. So for example, a really well-known formula is something called Kirchhoff's theorem, which counts the number of spanning trees of a graph. And it's actually the case that the number of spanning trees of a graph is the product, up to a constant, is the product of all of the Laplacian eigenvalues except for the 0, 1. So this is the sort of combinatorial information that you can get out of spectral graph theory, that it's actually an interesting combinatorial theory that's developed in parallel to the PDE theory we know and love from smooth geometry. You can also ask an identical question, which is, can you hear the shape of a graph? In other words, if I give you the eigenvalues of a graph Laplacian, can you reconstruct its topology or its connectivity? And sadly, the answer is still no. So for example, these are two isospectral graphs. Incidentally, I think a student in this course a year or two ago actually computed the spectra for these graphs that I'm showing on the slide and found for the definition of graph Laplacian that I gave you, this may not work out. There are many different variations of graph Laplacian that have to do with whether or not you normalize the rows and columns to sum to a particular constant. I forget which Laplacian definition this particular pair serves a counterexample for, but it turns out just about any reasonable graph Laplacian, you can find pairs of graphs with identical sequences of eigenvalues, which is too bad. So no, you cannot hear the shape of a graph. Okay, so now if we return to our outline one last time, we're finally ready to define a Laplacian on a submanifold of Rn. Okay, and so this is really the object that we're going to care about when we do shape analysis, because this is the one that's going to tell us the most interesting information, both about like triangle meshes, tap meshes, and stuff in low dimensions, and point clouds in higher dimensions. So we're going to spend quite a bit of time constructing this general operator and motivating it in a few different ways, based on the constructions that we've done in the first three, like based on the Dirichlet energy, and also based on this divergence of gradient interpretation. So let's take a quick break, and then we'll get started. All right, so let's get started with our definition of Laplacian, specifically for functions on surfaces and manifolds. So first we have to talk about what a function is. And just as a quick reminder, of course, a function is something that takes as input a point on our submanifold, like our bunny here, and assigns a number, a real value, to every single point. So for example, we might think of the color on this bunny as a scalar function associated to every point on the bunny here. We also defined many lectures ago the differential of a map, which is essentially defined through this equation that I've shown here in yellow. So if phi is a map from one space into another, then the differential of a map phi at a particular point P on my source domain is a function that is linear on the tangent plane to my manifold. So essentially what it does is for every tangent vector, it maps it to the directional derivative of phi in that tangent vector direction. That's what our definition of the differential of a map is. And in particular, we're just going to talk about differentials of functions which map into the real values. So nothing terribly complicated. So this is like giving us the directional derivative at P in the gamma prime direction of our function phi. Whew. Okay, so it's easy enough to compute the differential, and we made many different arguments that this is sort of the useful notion of derivative. Of course, if we want to define something like Dirichlet energy, we don't just need the differential, we actually need a vector, which is the gradient of our function. And thankfully, such a thing exists. In particular, what we're going to prove is a useful little proposition here, which says that if I'm on our m-dimensional manifold, big M, then there exists at every point P a vector gradient of f evaluated at P with the property that df at P is equal to a dot product. So basically, the thing that we're going to want to derive is that if I have a function f which goes from our manifold into the real numbers, and I look at the differential of f evaluated at point P, or rather, yeah, at a point P, and I give it a vector v as input. Remember, that's how we define the differential. That secretly, this is equal to the dot product between v and the gradient of f, where this is some vector which is associated to a point P, but not to v. Okay? And this is really just a fancy proposition that defines something you guys already probably knew existed, right? Which is just gradient vectors, right? So we compute gradients all the time on flat spaces. Here we're just double checking that it makes sense to talk about a gradient vector field on a curved domain as well. So for example, on this sphere here, if I have a function that's like -1 on the left of the sphere and 1 on the right-hand side, then these little hairs on the side of the sphere are giving the gradient field, which is this field of tangent directions, telling us how our function is increasing. Okay, so let's prove this little proposition really quick. So in order to do that, we're going to take a basis B1 through, let's see, my notes are a little bit wrong, but that's okay. Through Bm, if m is the dimension of our manifold, for the tangent space at P of our manifold. Because notice that this theorem sort of can decouple for every P. We're just sort of saying, fixing P, we want to make sure that there exists some gradient vector so that this relationship is true. Okay? You'll notice I'm holding my notes here so that I don't get this calculation wrong. Right, so we're going to define a particular vector. So we're going to say that AI is equal to df at P evaluated at the basis I. Okay? So essentially, we're just taking the directional derivative of our function f in each of the basis directions, and that's giving us a scalar AI. Okay, so now we're going to do an annoying calculation. So in particular, we're going to define a particular object. There are actually simpler ways to do this particular proof, but I want to sort of define something that's going to be useful in our discussion of Riemannian geometry later. So we're going to define a matrix. This is called the metric matrix with elements Gij, which are equal to just the dot products between the Bi's and the Bj's. Okay? And we're going to say that the inverse matrix, what we're going to do is we're going to use weird differential geometry notation so that you get used to it. So we're going to say that the inverse matrix, G to the -1 here, has elements G upper ij. Okay, so lower ij elements are the dot products of the B's, upper ij's are the inverse of this matrix. Okay, so now what we're going to do is just define a vector and then check that it's actually the gradient here. So we're going to define x to be the following. We're going to say that this is equal to the sum over I and j of A lower I, G upper I, J, B, J. By the way, I encourage you guys to all go back and see if you can work out the kind of matrix vector product version of this proof that doesn't use all these indices. This is just mostly for a little bit of review of how to do these index-based proofs. By the way, in Einstein notation, of course, I would just omit this sum here. And notice that that ends up kind of working out, right? Like there's every upper and lower index is repeated. X doesn't have any indices on it. So far, our equation kind of parses. So our claim is going to be that x is actually the gradient vector that we want. Okay, so now we're going to take any v, which is in the tangent space at P of our manifold M. Right, so what we need to show is this relationship here that I'll draw a little box around. Right, that if we evaluate df in V is equal to V dot, in our case, X. Okay, so we're going to write V in the same basis as everything else. So we can write v is equal to the sum over I of v upper I b I, like that. So this is just saying that like I'm going to write v in the basis b, which is for the tangent space, which I can do because v is a tangent vector. Okay, so now this is all our setup. Now we're going to do our big calculation here, which is just a bunch of index flipping. No fun at all. All right, so what we need is v dot producted with x, right? Because x, again, remember, we think maybe is the gradient of f at p, question mark. So we just have to double check. So, okay, remember that v, in fact, do you want to be fancy? I'm going to leave out our sums. Let's use Einstein notation for a change. So remember, Einstein says anytime an index is repeated twice, once upper and once lower, we're going to sum over that index implicitly. I'm departing from my notes, so this is going to be dangerous. Okay, so we have vi bi, like that. So this is implicitly summed over I, dot producted with, okay, so let's see. So we have x, and x is defined as this sum here. We've already used the index I, so I'm going to replace it with a different one, which is k. So we'll say that this is a lower k, g upper k, L, and then we got a BL. Okay, so we're just going to avoid I and j altogether in that second term. Now the first thing that we should do is figure out what's a scalar and what's a vector. Essentially the vectors in this expression are just the b's, right? Everything else here, you know, G is a matrix, but this is just one element of a matrix, so it's really just a scalar. And the VI's and the AK's here are scalars as well. Okay, so of course we can then write this as follows, right? So this is V upper I, A lower k, like that. And now, let's see, so we have the following. So we have G upper KL, like that. And we have BI dot producted with BL, but by definition that's G lower IL. Okay. And remember that this whole expression is summed over I, K, L. Did I miss anything? Nope, that's it. So it's a triple sum, but because we're being fancy and using Einstein notation, we left it out. Okay, so first of all, notice that, okay, so I and K are involved in our V and A terms here. But there's an L which appears here and is shared among these two matrices. In particular, this defines a matrix product. Right, so you can think of this as kind of like multiplying G inverse times G and evaluating it at element, well, the L is shared, so it gets summed and goes away. So this is just Ki. Okay, but remember, what is the inverse of a matrix times itself? Well, it's just the identity. So this whole expression is really just delta K equals I. So at the end of the day, what is this saying? Well, it's saying that really this whole expression v dot x is really just v upper I, a lower I, summed over I. And the reason we were able to do that is we just canceled a matrix and its inverse. Because again, remember that the inverse has elements with upper ij. That's what we wrote here. Okay, so remember what AI is, right? By definition, AI is df of bi, right? So this is vi df at p of bi, where b is a basis. By linearity, this is the same as df at p of v upper I, b lower I, like that. And by definition, this sum of v times b is equal to v. Okay, so this is d f at p of v. So what did we show? We showed if we took the dot product between an arbitrary vector v and this thing x that we defined, and notice that x has no v dependence, then what we actually got was df evaluated at p. So what did we show? Well, we showed that essentially this relationship is true. Now, in the course notes, I also give an additional detail, which is that no other gradient vector can exist in the tangent plane. So in fact, x is unique. So it's a well-defined thing to talk about the gradient of a function f as an assignment of a tangent vector per point on our manifold. So really what's going on, this argument was a little bit opaque, and that's a little bit on purpose because I want you guys to practice your Riemann notation as we slowly move into that area. But we can draw a bit of a picture of what's going on here. Essentially, all that's going on is like, if I took, so a very different proof of the same fact would be to take a local parametrization of our manifold at P. So here's our usual picture. And one thing that we can do is we can pull back our function. So remember that our function maps the manifold into the real values. So what can we do? We can actually define a function down here, right, by taking f composed with phi. So in effect, what this proof is doing, what you can double check, is we look at f composed with phi, which is a map from our region in Rm directly into the real numbers. We're going to bypass our manifold. We know how to compute the gradient of this, right? This is just like the vector of partial derivatives, right? Because now there's no curved space involved. And essentially all our gradient is just this gradient vector down here pushed forward by d phi. So you just multiply it by the Jacobian of phi. And so if you go back through this calculation on the left, you'll see that that's really all that's going on. And essentially these g terms are to account for the fact that dot products up here in our extrinsic space are not the same as dot products down here. And we have to be a little bit careful about that when we're moving from one place to another. So in any event, the high-level point here is that if we're given a function f, which inputs every point on our manifold, outputs a real number, then we can cook up a vector field, which is an assignment of a tangent vector to every point on our domain, with the property that is equal to the gradient of f, or in other words, that df is really the dot product between the input to df, like v, and this fixed gradient vector, grad f. So this, by the way, kind of closes the loop between differential of a function and this usual thing, the usual way we're used to differentiating multivariate things, which is by computing gradients. That's all we've done here. If you found this proof boring, that's because it kind of was. Like, it's almost tautological, but not quite. Okay, so let's erase this and move on. Okay, so now that we have a gradient operator, we can totally reasonably define the Dirichlet energy of a function on a surface. So what do? If we have a function on a surface, well, we can take its gradient pointwise. That gives us a vector field. We can take the 2 norm of that vector field, right? That's easy to do, just dot product with itself. And then take the surface integral of that using your favorite notion of surface integral from multivariable calculus class. And what you get is the Dirichlet energy of a function. And so that's like halfway toward defining a Laplace operator, but not 100% of the way, right? Because of course, a Laplace operator somehow is hiding in the Dirichlet energy, but it's not quite there. Now, in particular, here's kind of what's missing. So we can define a Laplacian inner product as follows, right? So essentially, if we have 2 functions f and g, then generalizing our expression for Dirichlet energy ever so slightly, we can write the inner product of the gradients of f and g. This is sometimes called the Sobolev inner product, as this expression on the top line here. And one pattern that I hope that you all noticed in the previous couple pieces of this lecture is the following, that essentially we defined Dirichlet energy, then we integrated by parts. And what we ended up with is that essentially the inner product of 2 functions, which are really their gradients, is equal to the inner product of 1 function with the Laplacian of the other guy. And that was useful. In fact, usually we kind of worked backward from the last expression here to the first one, because it told us that our operator was symmetric and positive definite. And it also was kind of motivated by finite dimensional linear algebra. So in particular, actually our graph Laplacian example made that really concrete, right? Because whereas we just spent a few minutes deriving what it means to be a gradient operator for a function on a manifold, on a graph is quite easy, right? So if we have some function per vertex, right, then df, remember, was our gradient function. And we just said that our Laplacian was d transpose d. And one way to kind of understand how we got there was to say, okay, well, what is our inner product analog in the graph case? Well, it's kind of like dg dot product with df, or the other way around, but it's symmetric, whatever, which is, of course, g transpose df, like that. And then essentially all I can do is, before we parenthesize this way, right? But now if I parenthesize this way, then what I get is g dot producted with this Laplacian matrix times f. And that was sort of our way of relating a derivative operator, like a first derivative operator, with a Laplacian operator. It's just basically a regrouping when we write this inner product here. And we can do a very similar argument here, but it turns out to involve a little bit of functional analysis that we don't have at our disposal in this course, namely something called the Riesz representation theorem. But the basic point here is that because we have this inner product which satisfies all of the conditions of being an inner product, you can kind of make an indirect argument that sitting underneath it is some operator delta with the relationship that I've written on the slide here. And that operator is called the Laplacian. Or in the curved case, sometimes we call this the Laplace-Beltrami operator, which is basically just the Laplacian operator associated to smooth manifolds. Now, this story isn't super satisfying, right? I got you half of the way there. We defined gradient. That led us to the Dirichlet energy. But then I kind of had to wave my arms a little bit to say, well, now that we have this quadratic form, it's just Dirichlet energy. Really, by doing a little bit of regrouping, we can get the Laplacian. This argument does hold water, but it requires some mathematical machinery we don't have at our disposal. But we can do a different thing, which is that, of course, Laplacian is the divergence of gradient. And so one thing that we can do is say, okay, well, we've defined what it means to be the gradient of a function on a surface. We can also define what it means to be divergence, and then we can just put the two together, right? We can say Laplacian is minus div of grad. So what we're going to do is I'll define divergence here, and then in an extra lecture segment that we're going to record after this clip, we'll go through a bit of motivation for where this formula comes from. The basic point is that if I have a vector field on my surface, so for example, this is in 3D, if we get rid of the 3 and replace it with n, then it becomes an m-dimensional manifold in Rn. Really nothing changes, except the 3's and the 2's. Where essentially the way that you can define divergence looks an awful lot like the flat version. So remember, if I have a vector field v in the plane, right, then the divergence of v is just equal to the sum of dvi over dxi. So in other words, like I take the x derivative of the first coordinate plus the y derivative of the second coordinate and so on. And so it turns out that we can do a very similar formula to define divergence of a vector field on a surface. So what do? We take the dv, so like we differentiate our vector field along the surface in each of a bunch of orthogonal directions. So the EI here is an orthonormal basis. And we sum together these inner products. And really, this is just a generalization of the formula here. And that will give us a way to take in a tangent vector field and output its divergence. Of course, the formula here is not super useful, right? It doesn't tell us that it's independent of our choice of basis EI. That turns out to be certainly the case. And we should check that it really, our Laplacian is, minus div of grad, as I've just repaired in the slides here. So in the additional lecture segment that I'll record, essentially I'll give you a motivation for this formula from the ground up, where we're going to do really a derivation that shows you that this is a reasonable definition of divergence on a surface and that it should satisfy some version of integration by parts. But we're going to defer on that until our extra lecture segment because it's another lengthy calculation, and I think we've done enough of those. So let's erase a little bit. Okay. So there are many different definitions, incidentally, of divergence. You can also obtain it in this sort of nice intrinsic way. This is the physicist version of divergence, where you take a limit of a little ball on our surface, or in our manifold more generally, and look at kind of the flux of a vector field out of a little ball relative to its volume. Turns out all of these definitions are equivalent to one another, although they're different levels of easy or difficult to derive. But in any event, in our extra lecture segment, we'll show one extremely heuristic kind of construction that tells us that our definition is reasonable. And that's it. So now we have a Laplacian on a surface. It's minus div of grad, and I've given you both div and grad, so that's a kosher thing to do. And in addition to that, one thing that we haven't argued carefully, but is true, is that this actually agrees with the definition of Dirichlet energy that we have, which is to say that the integral of f times Laplacian of f is the same as integrating the squared norm of the gradient of f, where we've defined Laplacian as minus div of grad, and the gradient is this thing that we derive with all the indices. In fact, there are many different formulas for gradient. Another way that you can do it is to say I can take a local parametrization of my surface, and as long as my local parametrization maps the kind of coordinates, like the xy coordinates in the surface case, to orthonormal directions on my manifold, then the Laplacian of the pullback of my function, remember that's like the, if I have a function on my surface, then I have a function on R2 here by like mapping to the surface and then reading off the function value. Essentially, computing Laplacian on the surface is the same as computing Laplacian downstairs, as long as we're careful to take the x and y axes to orthonormal vectors. If we like kind of skew our axes when we parameterize our surface, then this doesn't work out. But now that we have an operator, we can do all the same calculations we've already done. So for example, we can compute the eigenfunctions, and what we get are the vibration modes of our surface. Just to reiterate, this is the surface viewed as a two-dimensional manifold embedded in R3. This is not a volume. So for instance, here we see the vibration modes of this complicated lion model. And there's all kinds of fun physics experiments you can do as well. So one really famous one, which I think is kind of fun to watch for understanding vibration modes. So what happens in wave equation? Well, the surface is wiggling up and down in response to these vibration frequencies. But in places where the eigenfunction is equal to 0, these are called nodal domains, the surface actually isn't vibrating, right? Because it's vibrating up and down, but then on the nodal domains, it just happens to be this sort of stationary point as things pivot about. And so there's a very famous experiment where you can actually kind of observe the Laplacian operator by playing sounds next to a plate with a particular shape. Let me see if I can convince the YouTube video to load. Oh, that's too bad. Well, that's okay. So I've included links in the slides to two different examples. So essentially what's going to end up happening, I strongly encourage you to watch these videos because they're like mesmerizing, is as I play sounds adjacent to my plate that are the vibration frequencies of the plate, I pour sand on the surface of the plate. Well, the surface is vibrating up and down, so the sand is just bouncing off the surface, with the exception of the nodal domains, which are remaining still. So this really cool thing happens in this Chladni plate experiment, where all the sand concentrates close to the nodal domain boundaries, which are the places that aren't vibrating. So as you change the pitch that's playing next to your plate, you can actually see the Laplacian eigenfunctions kind of traced out by sand. This has actually been known to violin makers for a long time, because for instance, if you're engineering the top of an instrument, one thing that you have to put inside of your instrument is a sound post. And so like if I have, here's a profile view of my violin. If my violin is vibrating, then in a very infinitesimal level, as I play my violin, the upper surface of my violin is going to start vibrating in response to all of that sound. Well, somewhere I need to put a post from the top of the violin down to the bottom of the violin so the whole thing doesn't collapse, and to bring sound from one piece of wood to the other. This is called the sound post. And there's a lot of tension in your instrument, right? I mean, there's a lot of things that are holding it together so that it really is like this very tense piece of a couple pieces of wood glued together. If I place my sound post at an arbitrary place inside of the violin, in effect, it stops the violin from vibrating there, and that's no good. And so what you can do is like play a note on your violin, find a boundary of the nodal domain. So in other words, a place where it is not vibrating, right? Like the violin maybe vibrates like this, and then at the nodal domain, as the surface of the violin maybe wiggles, this point just stays still. And that is a good place to put your sound post because it's not going to get in the way of the sound that comes out of the instrument. And so one way to find that is actually to put sand on the instrument, play like the different tones that you would play in your violin, like the C major scale, and see where the sand ends up. And this would be a very old school way to do that kind of thing. And essentially what's going on there is you're looking at the boundaries of the nodal domains, which are the places where the eigenfunctions have 0 value. A famous theorem due to Courant actually tells you the number of regions that the nodal domains cut your volume into, which is kind of cool. So the nth eigenfunction of the Dirichlet boundary value eigenvalue problem has at most n nodal domains. And so for instance, like, the second eigenfunction divides your surface into 2 pieces if you look at the 0 level set, at most. Now, there are all kinds of connections to physics. We're going to recall these in future lectures as well. So for instance, the heat equation, which tells you how heat diffuses along a surface, also can be written in terms of the Laplacian. It's almost identical to the wave equation, but now instead of the second derivative of u in t, it's just the first derivative of u in t. Here's just our grab bag of other Google search terms as we talk about Laplacians. The Laplacian eigenfunctions of the sphere are things you've probably heard of. They're famous. They're called the spherical harmonics. They show up all over the place, for example, in molecular physics, and also just analysis of functions on spheres, for example, in Lie algebra, representation theory, and so on. And finally, the course notes go through this Weyl law in its most generality, which tells you something about the distribution of eigenvalues of Laplacian for different dimensionalities of domains, which is just one nice example between spectral calculations, geometry, and topology. And one last thing, sorry. Yet another place where the Laplacian appears is in mean curvature flow. So if we take the xyz function, like let's say that I have a surface, and I write 3 functions, which are just the x, the y, and the z coordinates of those points. If I take the Laplacian of that, then what I get back is the mean curvature normal, which we actually already derived in an earlier lecture. So if you go back and take a look at our earlier lecture, when we took the first variation of surface area, what we actually ended up computing was the Laplacian of the coordinate function, which is a calculation that we're going to defer on in lecture, but I encourage you to try and work it out at home. Okay, so in what ended up being 2 lectures, we'll divide this one over 2 course periods. Essentially, what we've done is introduce this object, which is the Laplacian operator, which very roughly takes a function on some domain. We talked about intervals, regions in Rn, graphs, and submanifolds of Rn. And it takes a function and it maps it to minus its sum of second derivatives. We showed that this thing is intricately linked with many other notions of smoothness and of wave propagation along domains. So for example, we started by motivating the Laplacian operator through the wave equation. Essentially, the Laplacian operator takes care of the spatial derivatives in the wave equation. And later on, we linked the Laplacian to measurement of Dirichlet energy. What that allowed us to do, for example, was when we looked at the eigenfunctions of the Laplacian operator, the eigenvalues correspond to increasing Dirichlet energy, which kind of tells us that low eigenvalue eigenfunctions of Laplacian correspond to very smooth objects in our domain, and as we compute higher and higher eigenvalues, they become more and more oscillatory. Now, we also kind of called out along the way different links between the spectrum of this operator, like its eigenvalues, eigenfunctions, and geometry and topology. For example, the Weil theorem, which tells us the link between Laplacian eigenvalues and dimensionality. And we're going to see many, many more of those in the coming lectures. So in our next lecture, we're going to go back through the Laplacian and figure out how to compute it on discrete domains, like meshes, point clouds, and so on. And essentially what that's going to do is bring our theory to practice. We're going to actually do the calculations that we've only done abstractly so far. And then after that, we'll talk about the many applications that are enabled by approximating Laplacian operators on different discrete geometric domains. So with that, I'll talk to you next time.